yesterday that we have started a system with generator connected to load, and then because of the nature of a fault on that power system, the power system becomes unstable, and most importantly it becomes unbalanced, and that unbalance is caused by the fault. It may be single line to ground fault, double line fault, or double line to ground fault. And because of that our calculation becomes very difficult, our analysis becomes very difficult. But Fortescue in 1918, 103 years ago, gave a theorem called three component theorem or symmetrical components that help us to analyze the unbalanced system, considering each and every phase and their voltages, currents, and so on. And when we do so, we find that for a three-phase system now, we don't no longer have the benefit or advantage of using one voltage, one current, one impedance at all. Now on, we have three voltages: positive sequence voltage, negative sequence voltage, zero sequence voltage. We have three currents: positive sequence current, negative sequence current, and zero sequence current. We have three impedance: positive sequence impedance, negative sequence impedance, and zero sequence impedance, and so on. So always they are going to be like that from now on. And from there we could see how we can define them, how we can denote those positive sequence, negative sequence, and zero sequences, all of them. So after all of that, we could get to this point that we will have positive sequence voltage VA1 for phase A, VB1 for phase B, VC1 for phase C. Similarly, we will get the other voltages for negative sequence of ABC, zero sequence for phase ABC. And we also can see that we can do that process in phasor diagrams. Adding VA1, VA2, and VA0 will give us VA. We can also do this from the analytical equations, meaning if we add them in terms of phasors, each of them are phasor. VA is a phasor itself in the first place, which we resolve into a number of components, three components: A1, A2, and A0. And then we can also go back from that side. If we add all these three, we will get back our actual phase voltage. So actual phase voltages are resolved into sequence component voltages. Actual voltages are resolved into sequence component voltages for analysis of that fault. Similarly, if we use the sequence component voltages, we can go back to the actual phase voltage. So that's the point that we were there yesterday. Now if we go to the next one, we'll take that equation that we just talked about. Let me copy and paste it on this next slide so you will be able to see it. I put it on this side so you can see it on the side, and how that equation is going to be utilized for the next step. So we have this equation VA, which is the actual phase voltage, which is maybe unbalanced or balanced, doesn't matter. It does not matter whether the voltage VA, VB, VC, they are balanced or not, but we still can apply Fortescue's theorem and get the sequence component voltages. And if we have the sequence component voltages, we will get back to the actual phase voltages. So from these equations, if you remember, we said we will always use the reference phasor when we express the voltages of each phase in the system. So first voltage is VA. What was our equation? VA1, VA2, and VA0. So our reference is phase A always, and in this case it remains because it's phase A, so it will remain as VA0, VA1 plus VA2 plus VA0. So they remain like that. The second equation is for the phase B, meaning the actual phase voltage of the phase B. So what it is, VB1, VB2, and VB0 are added. So VB1 is what? We did it from looking at the diagram. So if we don't remember, that's what I was trying to explain yesterday, that if we don't remember, This one is easy to remember. This one is easy to remember. VA1, VA2, VA0, VB1, VB2, VB0, VC, VC1, VC2, VC0. There is no problem. Should not be any problem. But now when we come to this VB1 to be expressed in terms of the reference phasor, which is VA1, VB2, which is need to be expressed in terms of the reference phasor, which is VA2. I don't remember this a relationship between VA2 and VB2, for example. So what I can do, I can go to the diagram here. I can go to the diagram here and I can find out, I can draw this diagram if I don't remember. So VA1, VB1, VC1, this is positive sequence. So after A, B will come, C will come, and B, C, now we have to relate them with the reference phasor, which is VA1. So it's 120 degrees, so it should be A VA1. This is 240 degrees, so this should be A squared VA1. Right, we can develop it like this. If we don't remember, don't need to memorize. Similarly, for negative sequence A, then it's negative sequence. So after A, C will come and then B will come. So VA2, VC2, let me extend it a little more so you can see it here. So VA2, then VC2 and VB2. So for VP2, it's 120 degrees. So it's AVA2. VA2 is now the reference, not VA1. VA1 is the reference for positive sequence. VA2 is the reference for negative sequence. So for VC2, it's 240 degrees. So it's A squared. So when we go there, we can write this equation VB1. We look at this. VB1 is what? A squared VA1. And then we put it there because our equation, let me reduce it a little bit. So VB1 is now A squared VA1. VB2, we look at it here. VB2 from the diagram, we can write it. So A VA2. And VB0 is there. VB0 is equal to VA0 because they are zero sequence. And then there is no phase angle difference between them. So the complex number operator A will not be present there at all. Okay, so when we're done with that, VB, we can go to the equation of VC, the phase voltage of C. So VC1, so we look at here, VC1 is AVA1, is coming from positive sequence. We can go back and write it from there. From A1, it's 120 degree in counterclockwise direction. So AVA1, we put it there. We look at VC2. VC2 is from negative sequence. It's where it's A squared VA2 because it's 240 degree from VA2. That's that one. And then VC0 will equal to V to VA0 because it's zero sequence, no phase angle difference. So we have this equation now. Now from this one, we will go to the next step. Is it clear to everyone how this equation now, these equations are now showing the phase voltages of A, B, and C. All the voltages on the right hand side of the equations are in terms of reference phasor of the phase voltage A, either A1, A2, or A0. The respective components are now expressed in terms of the reference voltage of phase A. So A1, all of them having A1, no VB1, no VC1, no VB2, no VC2, no VB0, no VC0. All of them are either having VA1 or VA2 or VA0. Is that clear to everyone?
Yes, sir.
Great. Let's go to the next step. In the next step, what we are doing, we are putting those equations, these three. Let me just copy them. So what we are doing here now, let me reduce the size a little bit. we are now taking these three equations. I need to reduce a little more, or I can go that side maybe. Yeah. So you have these three equations in the previous slide. Now we putting them in matrix form. We can put them in matrix form. So VA, VB, VC, and if we take them in terms of VA1, VA2, and VA0, they will be in the columns VA0, VA1, and VA2. Then we will have the 3 by 3 matrix inside, and it will look like 1, 1, 1, 1 squared A, 1 A squared. You can do this intermediate step by yourself, just practice. It won't take more than 2-3 minutes. So VABC is now represented by the sequence component voltages, zero sequence, positive sequence, and negative sequence. And this matrix is now called A, capital A, and it's called symmetrical transformation matrix because it helps us to transform, meaning the actual phase voltage VA, VB, VC can be presented or transformed into sequence component voltages VA0, VA1, VA2. So if we call it a transformation matrix, we can rewrite this equation as like this. So VA, VB, VC is equal to A times this sequence component voltages. In a simplified manner, we can write VABC. So ABC is the phase voltages, representing the notations for these three phases. So V is the voltage. Actual phase voltages can be represented by this transformation matrix and sequence component voltages. And this is called synthesis and equation. This is called synthesis equation. There is another equation that is coming, which is called analysis equation. This is called synthesis equation. The reason is that it synthesizes the voltages using the sequence component voltages, which are VA0, VA1, and VA2. So VABC is the actual phase voltage, V0, 1, 2 are the sequence component voltages. Right, so when we know the sequence component voltages, we can find out the actual phase voltages. Right, let's go to the next one. So from there, we can come to this opposite, like we said, it's synthesis equation. Let me just... So we did that synthesis equation. VABC is expressed using sequence component voltages. The opposite is analysis. So VABC is the one that we got with in the last slide, and using that one, we can now say if we want to know what are the sequence component voltages, how do we find it? It's easy from mathematics. So we will need to know the A inverse, that inverse of the transformation matrix, and we have the phase sequence voltages, phase voltages available or known to us. So how we find the inverse of that one? You did that in the mathematics modules, adjoint, and then the modulus and all those things. You can find it out. So now this equation is called analysis equation. This equation is called analysis equation, meaning it will show how the sequence component voltages are expressed using the actual voltages. Meaning the analysis equation shows how the sequence component voltages are expressed using the actual phase voltages. Is that clear to everyone?
Yes, sir.
If not, you should let me know so that I can try again, because we cannot afford, like I mentioned earlier the other day, we cannot afford to not understand these things. These are very fundamental. It will come, I don't know how many times in our real life application, as long as we will be working in electrical engineering field, all the time it will be there. So it's very important. So we have now synthesis equation. The synthesis equation, I'm trying to repeat it so that we absorb it synthesis equation is giving us the actual phase voltages ABC, VABC in terms of the transformation matrix A and the sequence component voltages. Whereas we have another equation, we will call it analysis equation, in which we will be able to find out what are the sequence component voltages that is expressed in terms of the transformation matrix, but in this case it's not the direct transformation matrix, but the inverse of it, and the actual phase voltages of the system that we are considering. And again, just to remind us, these actual voltages are going to be either balanced or unbalanced, but at the moment we are learning this theory because of unbalanced system, but it can be balanced as well, no problem. If it is balanced, there is no problem. We still can continue with this theory and work on and analyze what we want to analyze. There will be no problem. So if we expand this one, V012 is equal to A inverse times VABC, we will get to this matrix VA0, VA1, VA2 is equal to 1/3 times this matrix and times this matrix column, and from there we can write the equations VA0, VA1, VA2. So VA0 will be equal to 1/3 times VA plus VB plus VC, meaning if we have the actual phasors of those three phases ABC, we will be able to know VA0. Similarly, we will be able to know VA1, VA2, because all we need this side is the VA, VB, VC, and A is there. A is the complex number operator that we already know. It's 1 at an angle 120 degree, which is equal to e to the power j theta. Theta is 120 degree, which we also can express in rectangular form. Cos theta, j sine theta, cos 120 plus j sine 120 will end up having a value of minus 0.5 plus j 0.866. So if we have VABC, the phasors, we can find out all of them. Right, so that's that one. Is it clear to everyone?
I'm sorry, sir. VA, VB, and VC could be balanced or unbalanced. Okay, I just want you to know that.
Yeah. They could be balanced or unbalanced. It does not matter. It will not affect this equation. But interesting point will come when it is balanced. We will go back to where we started learning. Like I was mentioning yesterday, up until yesterday, there was no positive sequence voltage, there was no negative sequence voltage, there was no zero sequence voltage, and the same thing can be said about the current and impedance. We are talking about voltage only, current only, impedance only. And that's what happens when the system of voltages or the phasors is balanced. So if we used to say that VA, VB, BC is a balanced set of voltage, then we will arrive at a condition or a situation where there will be only one voltage, either VA1 or VA2. We will find that if we are using positive sequence and the system is balanced for the voltages VA, BC, then we'll say that VA0 will be equal to 0, VA2 will be equal to 0, only VA1 will be present there, and that will be that VA1 will be equal to VA, because it's a system which is balanced. And that's why we did not need to worry about VA2 and VA0. I have an explanation on this slide, so I'll show you that one. Okay, so it does not matter whether it's balanced or not. So we have so far talking about only voltages, but I was sometimes mentioning that it also applies with current. So we saw that VABC is equal to A times V012. VABC is equal to V012 times A. That's what I showed you, but it also applies to the current. So similar equation, no problem, no difference at all. Only V is now replaced by I. So IABC will be equal to A times I012, meaning the phase currents can be expressed in terms of the transformation matrix and the sequence component current, like sequence component voltages, sequence component current. So zero sequence current, positive sequence current, and negative sequence current. Similarly, if we look at the analysis equation, meaning the zero sequence, positive sequence, negative sequence currents now can be expressed in terms of the transformation matrix and the actual phase current. Again, these phase currents may be balanced or unbalanced, doesn't matter. The theory is so good, Fortescue's theorem is so good, it can encompass all the balanced and unbalanced conditions and sets of voltages and currents. Is that clear? So we can get the currents equation, IA like we did for VA, same thing. IA0 like we did for VA0, VA1, VA2, it's the same. So it was VA0 is equal to 1/3 VA plus VB plus VC. So IA1 was 1/3 IA, AIB, A squared IC. And meaning it's in terms of the phase currents and using the complex number operator A. So these are the equations for currents. And if you just replace the current by voltage, you go back to the voltage equation for actual phase voltages and symmetrical component voltages as well. So it's possible to go for the currents and voltages easily. But for the impedance, it's a bit complicated because impedance will come from the actual device or the equipment that we connect to our system. It can be a transmission line, it can be series impedance, it can be a motor, it can be a transformer. And when you do that, there are different conditions that comes with transformer connection. For example, when you have three-phase transformer, we connect them in star, we connect them in delta. Sometimes we leave the star ungrounded, sometimes we ground that star with some resistance, sometimes ground them directly, sometimes we ground that transformer through another transformer. We do a lot. So those conditions will come into the scenario when we will do the positive sequence impedance, negative sequence impedance, zero sequence impedance. They are not as simple as the way we did arrive the equations of currents and voltages for the sequence components. They are a little bit complicated, but we'll learn in step-by-step manner. So that is where I'm now coming. Like the point, if the voltages were balanced, what would happen to this sequence component voltages? So I consider this is a balanced system of voltages, VA, VB, VC. We considering positive sequence because VA is there, and then after that I drew VB here. So VB is coming, or phase B is coming after A. I'm just asking a question to all of you. How would I know that it's positive? How do I know? I'm explaining it that it's a positive sequence phasor diagram. VA is the first one, and then VB is the one that is following A, VB, sorry, VA. How do I understand that from this diagram? Do you understand that, everyone? Do you understand that this diagram is a positive sequence phasor diagram, and it is showing that if I say that VA is the first one to achieve any point on the sine wave, and then VB will come after that, VC will come after that. Do you understand that? If you don't, just let me know, I can explain it. Because these phasors are rotating, they are not stationary like as you see on the screen. It looks like stationary. VA is always vertical up. No, it's not like that. It's rotating 360 degree. It's just an instantaneous snapshot, always rotating. So how do I know that VA, VB, VC is the sequence? How do I understand that? Can you answer? Please answer. If you understand, please say yes. If you don't, say no. I'm looking at the chat box for your response. I'll continue only when I have some response from you. Naming convention moves in a clockwise direction. That's okay. That's understandable, but not 100% or easier way. From Zakari, thank you very much. Naming convention, but you need to combine that with the clockwise direction which you have mentioned. That's a very important point that you have mentioned, which is very good. Any other thing? They are rotating all the time. These phasors, VA is there, then it is rotating in clockwise, anti-clockwise direction. Naming convention is clockwise direction, but you see the direction of rotation, what I have shown here is anti-clockwise. The phasors are rotating in anti-clockwise, they are rotating anti-clockwise like I'm moving my mouse. They are not rotating in clockwise direction. So it's a good thing that you have mentioned, but not quite what I wanted or related. The phasors are rotating in anti-clockwise direction. Can you see the way I am moving my mouse is anti-clockwise? So what you need to do, I did not see anyone responding. What you need to do, you think just you are stationary, you are standing anywhere in between this 360 degree, at any degree. At any degree, you locate yourself. You imagine that you are standing anywhere. This is 360 degree. You are standing at any point of that those degrees, 360 degree. It can be fractional as well, no problem. You can say I'm standing at a point where the degree from this reference line x-axis is 101.235 degree. No problem. You can stand there. And you are stationary. You're not moving. Imagine that you stand at that particular degree, you can imagine, and be there, don't move. So what will you see? So let's say I'm standing here where my mouse pointer is. And if I am standing there, and what will come to me first? If I'm standing where the mouse pointer is with that four-headed arrows set, what I will see coming to me? Write down on the chat box.
B.
B. And then write down in the chat box B. After B, what will come to me? Then after VB, what will come? VC. Then it will be VA. So BCA, BCA meaning I will see ABC. Then I will see ABC. So it will be BCA, BCA will give me ABC. So you just can do the simple imagination and be sure. And now if you imagine that that phasor is drawn just like that, ABC as they are, but the direction of rotation is changed. Instead of counterclockwise, it's clockwise now. And I'm standing where I was standing there earlier. So I'm still standing here. And the direction of rotation of the phasors is now changed to clockwise. Then what will happen? What I will see first coming to me. Write down quickly. A, and then I will see C is going to come. Then B will come, meaning ACB. Immediately I get the phase sequence. Is that clear to everyone? You understand? So when you draw a phasor diagram, when you put those phasors names, labels, and the direction of rotation, imagine this and immediately you will know what are you drawing. Is it a positive sequence, negative sequence, or what is the phase sequence?
Sorry, sir.
Yes.
So you can specify the direction of rotation, or
yes, you can. You can. But once you have specified that, that will actually define now what is going to be the phase sequence.
Okay, so you chose anti-clockwise, therefore.
Yes, and anti-clockwise is the normal convention. People used to choose all the people, they choose the anti-clockwise. But you can choose clockwise as well. Then that will change your phase sequence. You understand, like I was saying, if with the same diagram, if I change the direction of rotation to clockwise, it will give me phase sequence ACB. Okay, you can choose it, but our normal convention is to choose anti-clockwise direction. Okay, so we can now move. So I'm considering these are the phasors or the voltages VA, VB, VC on the diagram with a sequence of A, B, C as shown with the direction of rotation and the magnitudes, the balanced voltages. So the magnitudes VA, VB, VC, they are same, equal to each other. They are displaced from each other by 120 degree. So from this phasor diagram, using the complex number operator A and the phase A as the reference, I can express all the three phase voltages VA, VB, VC in terms of the reference voltage VA and the complex number operator A. So our equation for VA will be equal to VA because it's the reference phasor that I have used. VB will no longer be expressed as VB but expressed in terms of the reference VA, and VB is where it's here 240 degrees, so it's a squared. VC is where VC is just after 120 degree from A, so it will be AVA. So I have now the three voltages expressed in terms of the reference phasor VA and using the complex number operator A. Now I go to those equations of sequence component voltages VA0, VA1 and VA2. And if we go there, we have those equations derived that VA0 is what? If VA0 is equal to 1/3 times the summation of all the three phase voltages VA, VB, VC. And if we go up there, we replace VA is equal to VA, VB is what? VB is a squared plus VA1, and VC is what? VC is AVA. And if we take the VA out, put it as a common one outside the bracket, then we'll find it's 1 plus A squared. And we saw in the complex number operator equation, the properties of complex number operator, let me go, yeah, that was that slide, that this is equal to 0. This is very useful, that's what I told you, that O1 plus S plus A squared is very useful, that reduces all calculations. So if we put it there, and then we find that this becomes 0. VA0 is equal to 0. So if we have a balanced set of voltages, then we find that there will be no zero sequence voltage. There will be no zero sequence voltage. Similarly, we can come to the equation of VA1 and we replace all those VA, VB, VC with in terms of the complex number operator A and the reference phasor voltage VA. It will become equal to VA. That's what I was trying to explain initially. Meaning there will be positive sequence voltage present, whose magnitude and angle will be exactly the voltage of phase A. If we come to VA2, we replace all those values that from here, and we'll find that VA2 is equal to 0, meaning there will be no negative sequence voltage. That is why in those first places where we are doing calculations, we did not need to worry about, or we did not need to know that there can be other voltages present, only one voltage. So if we used this actually in our second year, third year, first year calculations, we did not need to worry about VA1, VA0, VA2, because if we used VA, then that is the one which is present, and that is the only one. Other things were 0, they were absent. So if someone is absent, there will be no effect of that. But if the system voltages are unbalanced, then they will be present. They will no longer be 0. So we will have some VA0 and VA2. So that is why we did not need to worry when we have worked with balanced system of voltages. And in the beginning, we always start with balanced system of voltages. Is that clear to everyone now? And this also shows how symmetrical component theory is given by Fortescue is also applicable and justifies what we have been doing since the beginning of these three-phase voltages, and not using or not worrying, not knowing about negative sequence voltage and zero sequence voltage. Only using one voltage of phase A, and this phase A is also equal to phase B, phase C. Is that clear? Okay, let's go to some special case. We saw that if the sum of these three is equal to 0, then VA0 is equal to going to be 0. That happens in some cases. We might find that there is a system which is not balanced, but the sum of these three voltages can be 0. Then we will get VA0 equal to 0. It can happen in a delta connected system where some of the three phase voltages may become 0 and giving a condition where zero sequence voltage is going to be 0, although the system might not be balanced. So it can happen in real life power systems as well, that the system is not balanced, but the sum of VA, VB, VC is equal to 0 because they are phasors. And it can give that condition that zero sequence voltage can be equal to 0. Can I move to the next one? But if you have any question, you can ask. Let me give you a few moments before I move to the other section, which is going to discuss what happens when we deal with the calculation of power, because in our power systems, not only we do consider the voltage and current, we also calculate power, active power, reactive power, when it's single phase, three phase, balanced, unbalanced, does not matter. All the time we also need to know the power, because that is what we deal with in our power systems. Power is the one that we deal with. So what happens when you deal with powers and the system is unbalanced, especially, and we need to do the calculation for each phase power, because now the system is unbalanced, the voltages are different, the currents are different. So we need to consider the power for each phase, and then we add them together to get three phase power, and so on. So if we consider that we have a single phase power system and we want to calculate the volt ampere VA, which is the apparent power, so we use the symbol S, and I wrote it here one phase, meaning single phase VA that we are trying to calculate. Our normal convention is P plus JQ. And how do we calculate VI conjugate? I described that in the load flow studies. That is our normal practice, VI conjugate. So we multiply the I conjugate with the voltage and their phase voltages and phase currents. So we can calculate that for single phase. But when it comes with three phase, what we do, if the system is balanced, we can do this and multiply by 3. We will get it for three phase. But if the system is unbalanced, they are going to be different. So we cannot just calculate for one phase and multiply it by 3 because they are not same. So for three phase, but we have to consider it's a three phase system. We still can calculating the apparent power VA, and I wrote it as ABC, means three phase is involved here, ABC, and I wrote three phase to make sure that we don't forget. And how do we need to calculate? We need to calculate each phase separately and get the apparent power for each phase, and then only we add them. So it's now VI conjugate again, but for the respective voltages and currents. VA cannot be multiplied by IB conjugate, VA IA conjugate, VB IB conjugate, VC IC conjugate. Again, those VA, VB, VC, IA, IB, IC are the respective phase currents. If you don't understand phase current, phase voltage, just need to go back. Line voltage, line current, I described that in power systems 1, but again, if some of you has forgotten, you can just go back and check which one is phase current, line current back, because that will change when we go from start to delta connection. If you remember that, we cannot forget that. So just need to go back to that position again, because when you are saying these are the phase voltages, so we need to remember that when we are considering star connection, when we are considering delta connection. But in this equation, these are the phase voltages and phase currents. We cannot mix them. So when we have this equation written, we can simplify them and it will become like this. So VABC, IABC conjugate, and then we can transpose them and then write it in this manner. Simplified manner is like this: VABC transpose and then IABC conjugate. But from there, if we take our equations back and relate it to this equation in the previous slide, then we'll get to this ABC, VABC. We know VABC was what? VABC was A times B012. IABC was what? IABC is here. IABC was what? IABC was A times I012. So we put them here and do all this calculation for transpose and conjugate, and considering the properties of the complex number operator A, we will finally arrive to this equation, which will look like this. And in the next step, it will look like this. And in the final version, it will look like this. So it will look like this, the one that is highlighted there. And what it says 3 times VA0, IA0 conjugate, 3 times VA1, IA1 conjugate, 3 times VA2, IA2 conjugate. So what we do, we use the component voltages and currents, take them respectively, meaning VA0 is multiplied with the IA0 conjugate, VA1 is multiplied with the IA1 conjugate, VA2 is multiplied by the IA2 conjugate, and then we add them, multiply by 3. Then we get the total complex power of the three-phase system, which might again be balanced or unbalanced, doesn't matter. Because if it is balanced, there will be no VA0, IA0, there will be no VA2, IA2, and there will be only VA1, IA1, and that VA1 will be equal to VA, IA1 will be equal to IA. So that's why we were doing this calculation in the very beginning, that 3VA-IA is the apparent power, the total apparent power of a three-phase system. Can you see that? If we have had a balanced system, then VA0, VA2 will be equal to 0, only VA1 will be present there, and that VA1 will be equal to VA. Similarly, IA1 will be equal to IA, will give us 3VAIA. That's what we were doing up until last year. Is that clear to everyone?
Yes, sir.
That's great. Just absorb this. Should we take a break? Let's start. So we saw that we can calculate the complex power in terms of the voltage and the current using the sequence component voltages and currents and the respective phases. So VA0, VA0 should be multiplied with IA0, VA1 with IA1, and VA2 with IA2. And we also can verify from the equation here that if the system was balanced in the first place, but we carried out this calculation, if it is still making sense with what we have been doing in our earlier days. Yes, it does, because in that case VA0 will be equal to 0, VA2 will be equal to 0, meaning those two components will be absent, and VA1 will be equal to VA, IA1 will be equal to IA, and then it gives us VAIA times 3, meaning that's what we were doing. So it's the way we calculate the total complex power or apparent power, and that is why it's called the component transformation, meaning when we transform them using the Fortescue's theorem, the power does not change. That is why it's called power invariant. The power calculation will not change. It will still give us the same power that we would have calculated. So it's the same. Now we coming to very important section, which is going to consider the zero sequence component currents. It's very important to understand. Now it's coming to very specific. So zero sequence component current, how do we saw the equation? We saw it IA0 is equal to IB0 is equal to IC0, because they are zero sequence current. They are supposed to be equal, and they will be given by this equation: 1/3 times IA plus IB plus IC. So sum of those three current phasors multiplied by 1/3 will give us three values which are equal to each other: IA0, PA0, IB0 and IC0. Now we coming to consider the first case. If we have a delta connected winding. And why do we need to consider the delta connected winding? We get many cases in our real life, starting from motor. The motors, three-phase motors, all the three phases are finally connected to delta formation. It might be connected to star formation. We have lot of loads, either delta connected loads. We might have resistive, inductive, or RLC, whatever combination is there. We might connect them in star or delta. And especially when we go to the transformers, three-phase transformers, we always get them in many different configurations, like star transformer, star delta transformer, delta star transformer, delta transformer, and whatnot. All possibilities are there. So we need to consider each and every case, meaning star and delta. So we are starting with the delta configuration. So we have this delta configuration here. The nodes or the connecting points are here labeled as. You wanted to say something? I heard someone was saying something. There's nothing. It's okay. So we consider that there is a there are three windings that are connected in delta. The connecting points that is shown as A, B, C as the nodes, and there will be zero sequence currents. We are talking about zero sequence currents now. So zero sequence currents will be flowing in them. So IAB0 is labeled here. And why is it IAB0? Because it's flowing in the branch between A and B, and it's zero sequence current. So IAB0 is indicating it's a zero sequence current. Similarly, from B to C, BC0. I is for current, BC is for B and C nodes, and 0 is for zero sequence, and then ICA0 similarly. These are the branch currents, or the phase, each phase, and these are the lines. So this is phase actually. So IAB0 is the phase current for zero sequence, IBC0 is the phase current, ICA0 is the phase current for zero sequence, and these are the line currents: IA0, IB0, and IC0 going into the configuration of delta. It can be a motor, it can be a transformer as well, and it can be another load which doesn't have anything on the secondary side. It's possible. So IA0, IB0, IC0 are the line currents for zero sequence. So we want to now know what will be. It's written here IA0 equal to 0, IB0 is equal to 0, IC is equal to 0, but we want to see how they will be equal to 0. We want to find that one out. Now what we need to do, we need to apply Kirchhoff's current law at each and every node, those A, B, and C. Each of these three nodes will apply Kirchhoff's current law, and we'll find out that this line current IA0 will be equal to 0. This line current IB0 will be equal to 0. Also this current IC0 will be equal to 0. How we'll find that? We apply to this node A the Kirchhoff's current law, and we find that what are the currents coming in and what are the currents going out. We know the convention: coming in is positive, going out is negative. So IA0 is coming in. I showed it like that. You can choose another direction and you will find the same answer, which is I is equal to 0. So IA0 is incoming, ICA0 is also incoming, they are positive, and IAB0 is going out, so that's negative. I put it on the right hand side. So if we solve them, ICA0 and IAB0, they are same, that is shown there, because they are zero sequence currents on the phase. But if they are different, then this equation will not hold water at all. So from there we find that IA0 is equal to 0. Similarly, if we apply Kirchhoff's current law to this node B and C respectively, we'll find that IB0 equal to will be 0 and IC0 will be equal to 0. So from this, we'll have to now remember that if we have a configuration which is delta and the phase current or branch currents for zero sequence IAB0, IBC0, ICA0, which are equal to each other, then it gives rise to a condition where the zero sequence currents in the lines will be equal to 0. So no zero sequence current will flow in the lines if there is a delta configuration where the branch currents or the phase currents for these three windings of the delta configuration are same. Then it will give rise to a condition where there will be no zero sequence current in the lines. Is that clear?
Yes, sir.
Okay, that's good. So we'll remember this, that when we have delta connection, if the branch currents or phase currents inside the delta configuration, they are of equal magnitude, the line currents for the zero sequence will be 0. None of these phases ABC will have zero sequence current. We're talking only about zero sequence current, not positive, negative. They might be different. We'll have to remember that. Now from delta, we want to go to see what happens if we have star connection, not delta connection. So for star connection, we have a number of combinations. The first one is star connected winding with neutral isolated from the ground, meaning the neutral of the star point. Whenever we connect three windings into a star configuration, we will have a neutral point which is labeled here as small n, and we might choose to leave that as it is, meaning no connection to nowhere. We can have option to connect them to the ground, to somewhere else. We will see how it goes and why we do so. So this is the first case. The neutral point is left just like that, is isolated and isolated from the ground. Normally we connect neutral points to ground to keep the voltage of the neutral point at the ground voltage, which is normally supposed to be 0. So this is the case. What we find, we again find that these are the currents here that will flow because it's star connection. So whatever current we are considering here, IA0, IB0, IC0, they are again line currents. But what will flow in between A and N, B and N, C and N will be the phase currents. So these are the lines, and what will be flowing here is going to be the phase values, B A to N, B to N, C to N. So in this case, because it's star connection, we can see the line values will be equal to phase values. That's why we see that we use that formula, that line current is equal to phase current in star connection. So in this case, what is going to happen, the phase current, normal phase current IA, IB, IC is going to flow into the neutral point and they sum up to 0 always. But we have this equation for zero sequence current, IA0, IB0, IC0, which we calculate from the phase current 1/3 times IA plus IB plus IC, and this is equal to 0 from this equation. So what happens here, IA0, IB0, IC0 again becomes 0. Meaning if we have a star connection and if we find that the sum of sum of phase currents IB, IC and IA is going to go to the neutral, going to give us the value of 0. No zero sequence component of current will flow in the lines as well as in the phases. So in the lines is here, in the phases. So IA0 will be absent. So in the phase it will also be absent. So no line current or no phase current of zero sequence component will flow in the lines and phases if we have a star connection for three-phase winding which is isolated from the ground. If we have a star connection of three windings with its neutral isolated from the ground, we will not get any zero sequence component of current in the lines as well as in the phases. Is that clear to everyone?
Yes, sir. Yes, sir.
Good, thank you very much. So we can now go to the next one, in which is still the star connection. Like I said, we can have different configurations, different types of applications in our power systems. So the next case is that it's still the star connection, but now we connecting the neutral to the ground straight away solidly. We call it neutral grounded solidly, meaning it's a piece of wire that we used to connect the neutral of the star point to the ground solidly, meaning we assume that the resistance of that piece of wire that we are using to connect the neutral to the ground is very, very small, possibly 0, but it won't have a resistance value of 0 or impedance value of 0. It will have some resistance or impedance, but we can ignore that. If we ignore that, we can say that we have solidly, meaning if there is any current if there is any voltage present at the neutral point, it will cause some current flow to the neutral. So this is called neutral solidly grounded. Again, those conventions are shown here: IA0, IB0 and IC0 for the zero sequence current in the line. And again, they will enter the phases, and we might have a current here which is the neutral current, and that will be calculated. It's written here, it's 3IA0, but we'll see how we arrive at that equation that neutral current is equal to 3 times IA0. So this is the same diagram that I copied and pasted because it helps us to see, because if it was previous slide I would have to go back and show. So again, we know that these three-phase currents IA, IB, IC will give us the neutral current, and we know this equation from previous discussion that IA0 is equal to IB0 is equal to IC0, which is also equal to this equation 1/3 times IA, IB, IC that we got from symmetrical component analysis, and IA, IB, IC is equal to this neutral current. So that's what we get in, and that is why we can now say from this equation neutral current is 3 times IA0, meaning if the neutral is solidly grounded, there will be a current flow that will be equal to 3 times IA0, 3 times IB0, or 3 times IC0, because IA0, IB0, they are same. So that's what we need to now remember, because IA0 is now no longer 0, IB0 is no longer 0, IC0 is no longer 0, but it has a magnitude which is 1/3 the neutral current. Or if we want to know the neutral current that will flow, will be equal to 3 times either IA0 or IB0 or IC0. And this neutral current is very important for us to know. If that current flows, we need to do something. Sometimes we use it for protection, and sometimes we try to see why the neutral current is coming there and what could we do, or what could be the consequence of that. Right, so if we have a star connection, neutral grounded, IA0, IB0, IC0 will be present, and we can calculate that. Now it's the same case, but we considering that there is an impedance present in between the neutral point and ground, like the short piece of wire that I was considering or mentioning, to connect the neutral point of the star connection to the ground has some impedance which we cannot ignore. Then we consider that impedance to be labeled as Zn. N is for neutral, and Z, simple Z, are the impedances of each phase. Z is the impedance of each phase. Then what will happen? And in this case, we need to find out the equation. So that's why I show all those respective voltages VA, VB, VC, and the phase currents IA, IB, IC flowing into those star point or the neutral point through the impedances of each phase, and the ground point is shown as G. So from this we can write the equations of voltages and arrive at the condition what happens. So if we look at this diagram, I copied and pasted again for us to see it easily. The voltage is being applied here, applied there, and they finally reach this ground point through this impedance of the phase and the impedance of the piece of wire that is connecting the neutral point and the ground. So we can see that IA times Z and IN, which is the neutral current, times Zn is going to be the voltage between the point A and G, meaning the node A and G where the phase voltage A is being applied. So we can simplify it like this. Similarly, you can write the equation for the phase B and phase C, Zn, In, and then the other equation for the VCZ. Considering the expression, I can again copy this this figure for us to see how they are coming like that. Right, so VAN, VG and VCZ can be expressed in terms of these impedances and the respective currents, looking at the equations. So when we done that, then we can write them in matrix form. And now that is what I was explaining, that impedance is not that straightforward like we are getting sequence component voltages and currents. They are much more complicated. So what we see now, it looks like this matrix where the voltages are here and the current is here. So this is V is equal to IZ equation, which is our normal equation. So this is the impedance that will be giving us positive, negative, and zero sequence impedance. So when it comes like that, we need to do some manipulation a little more. So as this V is equal to IZ, so we can say phase voltage is equal to phase impedance times phase current. So phase voltage is equal to phase impedance times phase current. So the phase voltages are here, phase currents are here. This is the phase impedance matrix. So for three phase, we can write down the simple equation just like that: three phase voltages, three phase impedance, three phase currents. We can also write it like that. And now we want to use the transformation. If we remember, VABC was equal to A times V012. We also remember the similar nature of the equation for the current. IABC will be equal to A times I012, which are the respective sequence component currents. And if we put them there in that equation, then we end up having Z012 is equal to like this: A inverse times ZABC times A. And this Z012 is called sequence impedance matrix. And it's, you see, it has three terms now. The phase impedances is there, the inverse of the matrix A, and matrix A itself is there. So if we put all these values now here, we will find out what is going to happen. This is the ZABC, the one where my mouse pointer is. This is A inverse. This is the A. So if we manipulate those, then we find that we finally end up having Z012 is like this. So it's Z plus 3Zn 0 0 Z 3 0 0 0 Z. So This is the sequence impedance matrix, and it comes like that. So if we derive that, again we replace it like this from the previous one, and we write V0, V1, V2 for voltages of sequence components, and I0, I1, I2, because we know this equation V012 is equal to Z012 is equal to I0. So we can end up having equation like this, separate equation for each of those sequence component voltages, and we see that V0 is equal to Z plus 3Zn times I0, which is equal to Z0 times I0. V1 is equal to Z times I1, which is equal to be written as Z1 times I1. V2 is equal to Z times I2, and Z is now represented as Z2. So from this, what we see for the zero sequence, the neutral impedance is present, and not only that, it is multiplied by 3. So whenever we consider that there is an impedance in between the neutral point and the ground, that will appear in the zero sequence voltage current equation multiplied by 3, and we can calculate the V0 as Z0 times I0, where Z0 will be the sum of the phase impedance and the impedance of the neutral multiplied by 3. But for positive sequence voltage, only the phase sequence, as only the phase impedance is present there, and in that case we can say that the positive sequence impedance is nothing but equal to the impedance that is present in the phase. Similarly for the negative sequence, we can find out the voltage. Similarly for the negative sequence, sorry about the phone ringing, Z times I2, which is the phase impedance, times the negative sequence current, and the negative sequence impedance Z2 is nothing but the impedance that is present in the phase. So from there we can see that when you look at the equations of V0, only I0 is present, V1, I1 is present, V2, I2 is present, and they are called independent of each other. So V0 can never be depending on I1 or Z1. Similarly, we can say V2 will never be dependent on I0 or I1 or Z1. They are independent of each other if we look at the equations carefully. Is that clear to you?
Yes.
Okay, thank you very much. So I think let me, these are the same explanations shown here. From there, those equations, this V0, let me copy and paste these equations in the next slide, so I can try to go for these diagrams. Now for power systems fault analysis, if you remember in power systems 1, we needed to draw the reactance diagram, which we also have to do in this chapter as well. So from equations we will have to draw the diagrams. So we have this equation V0 is equal to Z plus 3Zn times I0, V1 equal to Z1 times I1, and Z1 is equal to Z, V2 is equal to Z2 times I2, Z2 is equal to Z, the phase impedance. From there we draw sequence networks, and in this case it will be 3 networks, corresponding to 3 sequence components, positive, negative, and 0. So in power systems 1, we drew one reactance diagram because it was only positive sequence, which was equal to either A or B or C. But here it's not that. All of them are there, positive, negative, and 0. So we'll have to draw 3 sequence network for each of them. So first one is the 0 sequence. So how do we draw it? From the equation, V0 is the voltage There is current I0 flowing, so we show the I0 flowing. And what are the impedances? Z and 3Zn, they are added here. The plus sign meaning the impedances are in series. We write that Z0 is equal to 3 plus Zn times 3, Z plus 3Zn. So that's the zero sequence network. For positive sequence network, looking at the equation, V1 is the applied voltage, I1 is the current that is flowing, and impedance is Z1, which is equal to Z. For negative sequence, we do the same. The V2 is the applied voltage, and Z2 is the impedance, which is equal to Z, and I2 is the negative sequence line. So these are the sequence networks that we will have to do for each and every power system that we want to analyze if the system is unbalanced. This is only the beginning and very simple still. But what we notice, they are independent of each other. Respective currents, voltages, and impedances are shown on the diagram for each of them. Respective voltage and current and impedances are shown there in conjunction with the polarities plus minus. So the current is shown. It has to be shown properly in the diagram, otherwise we will make mistake in the following steps and our calculations will be wrong. So from there we can describe, this is what I was describing, so we can read that later on. Now I'm coming to, okay, let me ask if you have any question on this one before I go to the representation of delta to star. Any question? Okay, no question is fine. Now we coming to a conditional situation. Sometimes we have a delta connection and we want to check what happens if we represent that delta to a star, and we do so many times. That's why we were taught about the delta star conversion or star delta conversion values for resistance and impedances, capacitors, all those things connection in second year, third year time. So in this case, we assume that we have a delta configuration where the impedance is labeled as Z delta. I just generalized it. Z delta meaning this the impedance when it is connected in delta for a three-phase configuration, and when we will have converted that delta connected impedances into a star, they will be having a value of Z delta over 3, and I'm sure you will be able to find out that by yourself. How you do that, I showed it in third year. So we have this Z delta over 3 when we have drawn the diagram for a delta connected system into a star which is equivalent to that delta. So what happens with that system? We'll draw this diagram for the sequence network. Remember that I said not only the equation, we also need to draw the diagram for power system fault analysis, and in this case it will be 3 diagrams, positive, negative, and zero sequence. So when we have a delta connected system, if you remember, there will be no zero sequence current flowing in the line, but zero sequence current will be flowing in the branches of phases. That was the first one. When we have star connected, then zero sequence currents will not be there. So when we representing and drawing the zero sequence network, what we will show? We will show the respective voltages and currents and impedances. So voltage, zero sequence is V0, I0 is the current, impedance is Z delta over 3, but the current will not flow because it's delta connected in the line. There will be no zero sequence current flow. So what we do, we show an open circuit here, and impedance, actually what will happen in zero sequence impedance, it will be infinity. That's why it will not allow any zero sequence current I0 to flow in the lines because it's delta connected originally in the first place. But for positive sequence and negative sequence, they will be present. So we consider V1 for the positive sequence voltage, I1 for the positive sequence current, and the impedance is again Z delta over 3, but that will now be equal to Z1 because we need to represent them respectively, because it's positive sequence network, so it should be Z1. For negative sequence, it's V2 the voltage, I2 is the negative sequence current, Z delta over 3 is the impedance, but that impedance is now called Z2 because it's a negative sequence network. Is that clear?
Yes, sir.
Yes, sir. Or people have already left? Oh no, 2 people have left, so that's fine. So if you have any question on this, you can ask. Otherwise, I will. I will stop it here. But I want to answer that question related to the frequency that I said last week. I will answer. If you have any question up until this, you can ask. Okay, we don't have, which is good. Now I want to mention that there was a question that was asked on the frequency. South Africa has 50 hertz, other countries have 60 hertz, and some other countries are using both 50 and 60 that I tried to explain in the previous class. But there was a question I thought was also embedded in that one, but it was not asked. How do we choose it to be, or why do we choose it to be 50 or 60 and so on? It's a very difficult task actually in the first place, or from the very beginning when the scientists or the engineers were trying to get to this frequency 50 hertz and 60 hertz. First of all, this 50 hertz and 60 hertz, whatever number of this frequency we are choosing, it has this relationship with F is equal to Pn by 120 degree that you have learned from the fundamentals. F is equal to Pn by 120. P is the number of poles of the generators and motors, and N is the rotational speed, number revolutions per minute, and that gives the frequency. So we can say that N for the motor will be determined by the choice of this frequency, or for the generator F will be determined by the number of poles and revolutions per minute of the generator rotor. So it's N is for motor. The speed of the motor will be determined by the frequency. The motor cannot determine the frequency comes from the generator. Similarly, the generator cannot determine the frequency. Generator is run at a particular frequency by the operator or the engineers, and that determines the frequency. Now, how you choose that frequency to be 50 or 60? Can it be 10 hertz or 100 hertz? Why not 10 hertz or 100 hertz or something like that? So for that purpose, what we need to do, we need to look at what we connect to, because this frequency now is connected to the generator. So when you look at the frequency and we find that it's coming from the generator, it's not coming from anywhere else, it's coming from the generator. So what frequency we can use? Can we use 10 hertz or can we use 100 hertz? Or why do we settle it to be 50 hertz and 60 hertz? So if we, let's say if we use 10 hertz or less frequency as compared to 50 hertz, what happens? Say we have loads. What type of loads? Let's say we have light bulbs, we have motors and things like that, right? So if we put a light bulb for the first example, what will happen if you connect an incandescent lamp? Now those olden days lamps, we still not using them much, but it's still there, because these days we have LEDs. But before that, what was happening in incandescent, we have had arc lamp, we have mercury vapor lamp, we have sodium vapor lamp, we have fluorescent lamps. All different types of lamps came before LED came in to the scenario. So incandescent lamp, what happens when we connect an incandescent lamp to a generator giving a frequency of 10 hertz or giving a frequency of 50 hertz? What happens to that lamp? Can you imagine that? Anyone?
Sorry, can you repeat your question?
Hmm?
Can you repeat the question?
My question, I have an incandescent lamp. I connect it to two generators. One is having 10 hertz, the other one is having 50 hertz. What I will observe? Or make it simple. I'm connecting a lamp to a generator which is supplying very low frequency. Let's say 1 hertz. Generator frequency is 1 hertz.
Will the lamp not like flicker on and off?
Yes, that's the point. Why will it flicker? If we go back,
the power supply is only coming on at a certain frequency. So
it's
like
always on certain frequency, but why will it flicker? If you make it 50 hertz, 100 hertz, it's also certain frequency.
yeah, well the frequency is slower, so
Yes.
at 50 hertz we won't notice the flickering because it's the time spacing smaller.
No, we will not notice time space is smaller, it's correct, but we need to be a little more specific. Why? Why we will not notice it at 50 hertz or 100 hertz, while we will probably notice it at 1 hertz?
Because at 1 hertz, obviously, like it's only coming.
What is hertz? Let's go back to hertz. What is hertz?
Well, it's how many times the wave passes a certain point, basically. So
Yes.
1 hertz will only be once every 1 second.
It's the time related to complete one cycle, right?
Yes, sir.
Number of cycles completed per second, that comes into the scenario. So if you say 1 hertz, what does it mean in that way?
It means that 1 cycle will be completed every second.
Yes, in 1 second, 1 cycle will be completed. And what will happen in each cycle?
The light will turn on and
No, just imagine about the sine wave of the voltage that we are talking about. Just imagine of the sine wave. There will be 2 zeros.
Yeah.
So every time you will observe 2 zero, meaning at that point of time, the light will not illuminate. It will be dark. That's why we see that flickering. But if you increase the frequency, what will happen? They will come more frequently. And that is related to persistence of vision. Do you remember that at school sometime they taught us? Huh? Do you remember that? Put your mic on.
So I don't think they taught us that, but we understand what you're saying.
You don't think?
I don't think they taught us that, but I understand what you're saying.
They should have taught us, for sure. 1/10 of a second.
No, I understand, like, you can only perceive motion at like a certain rate until...
So if it goes on and off, within that 1/10 of a second, we will see it flickering. But if it goes on and off, within that 1/10 second, then we will not see it flickering. That's what happens when you choose 50 hertz. If we lower the frequency at some point of time, you will see that those lights that we see in the decoration, when you have wedding, this and that, they put some lights. They actually, we call them automatic lighting. We like them so much when we have those kind of things. Didn't you see that?
Yes, sir.
Actually, what they do, they decrease the frequency
so that you can see it go on and off.
Flickering, and we like it because we put it for decoration. But if it was for normal day, normal life, flickering lights, we don't like it because it disturbs our eyes and we cannot work when it's flickering. And there are other problems in industry and processes as well. So that's why we could not go for lower frequencies. This is a problem for incandescent lamps, in arc lamp, vapor lamps, and all lamps. So we had to go up to a value where it's not going to flicker at all. And again, when we think of frequency of the generator, we cannot forget about the speed of the generator. The frequency will be determined the speed of the generator at which we are running. So whenever we want to increase the frequency, we have to make sure, because the generator has number of poles that is fixed, we can use either 2 pole or 4 pole. Now we have to change the frequency to a particular value so that the frequency is such that it doesn't cause the lamps to flicker. So that is where one trade-off was there. Now, if I leave this lamp alone, because now we can increase the frequency and stop the flickering of the lamps. But if we go to a motor, like I said, we can have a light bulb and we can have a motor, or we can also have a transformer connected to the generator for stepping up or stepping down the voltage. So what happens to those motors and transformers? When you connect a motor and a transformer to the generator, what happens? Motors and transformer, both of them have windings in them, either single phase or three phase, doesn't matter, and those windings represent some sort of impedance. It's not going to be R simply at all. They will have some inductance in the winding. Is that what you know, that a motor cannot have purely R in it?
Yes, sir. That's true.
Okay, but you need to know where that inductance is coming from. That is a big question that I'm asking. I'm always willing to take question. I want questions from you, but I am asking you this question that you must know, where is this inductance coming from for a motor or a transformer? So you'll find out that one. But if you cannot find out, let me know, we'll discuss that. So now when we go to the transformer and the motor, we find that inductance is there. Now there is a certain inductance that comes from the motor or the transformer that we have connected to the generator. Think about the frequency now. What happens if you increase the frequency? What will happen? The motor or the transformer that we have connected to the generator has certain inductance, but we are increasing the frequency of the generator. Let's say we are going from 50 to 60 hertz with the same inductance. What will happen? You know this answer for sure. You just need to tell me.
The reactive power will
No,
increase.
not that far.
The reactance.
Being simple, you have an inductance and you have increased the frequency from 50 to 60 hertz.
The inductance, the inductive reactance will increase.
Yes, that's the first step. Because you have inductance. Inductance is what? It's L. And from L, what you calculate in the immediate step? You calculate the inductive reactance X, which is twice pi times FL. So if you have L constant and you increasing the F, so what will happen? The inductive reactance will change. Or if you increase the frequency, the inductive reactance will be more. Because of that inductive reactance, what will happen to the impedance? The next step is impedance. Z value will
Change.
increase. If the Z increases, what will happen? If you keep the voltage of the generator constant, now you come to the generator voltage. If the voltage is constant, Z is increased because of increase in frequency. What will happen?
Current will decrease.
Yes. Then the next step is power. That is where Callum was talking about. Power will happen to what?
There'll be a decrease in power.
Yeah, think about current, power, and when it comes to power, you will think about both power, active power and reactive power. Right? So
Yep.
there is a challenge when you increase frequency for this type of loads, inductive that are coming from either motor or transformers. So that's why they tried as much they could, and they standardized the frequency to a certain value of 50 hertz to 60 hertz. Now again, running the generator at a low speed, like if we consider the 10 hertz or 20 hertz, is also a challenge, because those generators are being run by the use of primary sources of energy, like the main one is the sun, and that gives us many other sources like coal, wind, or nuclear power, and all those other things, water. So if we take those various types of sources, it becomes challenging. For some, it's very challenging to run the generator rotor at high speed. For some, it's very challenging to run them at low speed. For example, if you imagine of a wind turbine, it's very challenging to run that generator rotor at a very high speed, because it will be storming, tornado. You're running the generator at very high speed at tornado, which is good, but your building and everything will die before we use electricity. It will always be running at a lower speed, which is good for wind turbine. But if we look at the steam turbine, thermal power plant, it's very difficult to reduce the speed of the generator, because we have a lot of power at the input, and we need to use a turbine to make sure that we can run it. In olden days, before we came to the steam turbine generation invention and using the steam turbine for generation, there were steam engines in the first place actually, and they would start immediately at very high speed, 100,000 rpm. We cannot reduce it. For that, to reduce the speed from 100,000 to 3,000 rpm or 3,600 rpm corresponding to 50 hertz and 60 hertz was a very big challenge. So we needed to use the fundamental laws of Newton's laws of motion, and use the reaction from Newton's laws of motion. So we got two stages and more stages, impulse turbine, reaction turbine, and we use the reaction more and more to reduce the speed to that value of 3,000 and 3,600 rpm to give us 50 hertz or 60 hertz. So it's a bit challenging from many directions. Looking at the light bulbs, which are incandescent or arc lamp, they will flicker. If we look at the impedance, they will increase if we increase the frequency. Also, I'm sure when you run the motor or the transformer, you hear the buzzing sound is from magnetostriction that happens when you have core winding. They will start buzzing, humming sound that we hear when you go to substation or nearby a transformer, which we put our ear there. In a situation, we will hear that noise that comes from the frequency, and then we come to the generator, at which speed we can run them. For some generators, it's challenging to run them at low speed. For some generators, it's challenging to run them at higher speed. So that's why they standardized the frequency to a value where it is possible to go and mitigate all the problems that we might have from all the loads that are connected to the generator, because we cannot have light bulbs and we are going to have motor and transformer. It's not possible. We cannot have only light bulbs and we don't have motor and transformer. That's also not possible, right? So that's the challenging part of that frequency. Is that okay with you? Do you understand this part?
Yes, sir. Thanks.
Okay, I will talk about that other question that was asked. Sahil actually asked that question. It was about the harmonics and all other things related to it, meaning the sources and how we can mitigate them maybe a little bit. I will discuss that in the next class. Thank you.
Thank you very much, sir.
For your attendance, and keep well. We'll meet next time.